following is the apparatus used to study anode rays. A closed tube. The air in the tube has been pumped out, so the tube becomes a vacuum tube. The metal plate on the left side will be connected to the positive pole of the DC voltage source. We can call this metal the anode. The metal plate on the right side will be connected to the negative pole of the DC voltage source. We can call this metal the cathode. Unlike the anode, the cathode metal plate has a hole that penetrates the surface of the other side. The actual hole is so small, it cannot be seen with the naked eye. This hole looks big just for animation purposes. Between these two plates, there is a space. In this chamber, hydrogen gas is injected in a certain concentration. We can say that this gas is a low-pressure gas. These are the components of the apparatus used in this experiment. Now connect the electrical circuit and turn it on. On the surface of the cathode, a negative charge will accumulate. On the surface of the anode, a positive charge will accumulate. At a certain voltage value, electrons from the cathode surface will move towards the anode. Why don't electrons move to the right? Because negatively charged electrons will experience Coulomb's force towards the positive charge, or to the left. On the right, there are no external forces. During its movement, these electrons will collide with hydrogen gas molecules. Electrons in the hydrogen gas will bounce out towards the anode. At this time, the hydrogen gas molecules lose electrons and become positively charged particles. Particles with positive electrical charge will experience Coulomb forces towards the negative charge, or to the right, because there is a negatively charged surface there. Positive electrically charged particles will move towards the cathode. However, there are several holes in the cathode. Positively charged particles can pass through the hole to the other end. Well, the trajectory of this particle is a straight line. We can name this movement of particles as rays. Anode rays. Because it is as if the light comes from the anode. How do we know that the anode rays are positively charged? If we still remember the cathode ray experiment, we can place parallel plates at the right end. Just assume the top plate is connected to the positive pole of the DC voltage source, and the bottom plate is connected to the negative pole of the DC voltage source. Then the light will appear to turn towards the negatively charged plate. This is proof that the anode rays have a positive charge. In some references, these rays are known as Canal rays. Well, the scientist who researched Canal ray was Eugen Goldstein in 1886. Using a method similar to Thomson's experiment, Eugen Goldstein was able to calculate the charge-to-mass ratio, or E per m, of the anode rays. It turns out that the value of E per m is not just a single value. This value has several different values, depending on the type of gas used. Because it does not have one value, we cannot say that a ray channel particle is a single particle. Because it does not have one value, we cannot say that a Canal rays particle is a single particle. Rutherford researched the Canal rays experiments further. In 1920, Rutherford succeeded in identifying a single positively charged particle, known as a proton. So scientifically, the discoverer of the proton was Ernest Rutherford. However, Eugen Goldstein is still known as the inventor of Canal rays. Thank you for watching this video. And don't forget to watch the next video.